We're going to look at what ultrasound is, how it can be used in a couple of medical applications, and what are the benefits and drawbacks of using ultrasound for those applications. Now, just as a little background, we need to understand what we mean by ultrasound, and to help us along we just need to think about firstly what sound is. And sound is actually any material or object that vibrates, and if it vibrates enough it can create a sound, and we measure that sound by looking at its frequency, and frequency just means vibrations per second. So the number of vibrations per second is the frequency. It's measured in hertz, and hertz just means vibrations per second. And we can have a very high frequency, which means a high number of vibrations per second, or we can have a low frequency, and both of these will relate to the type of sound that you have. So at the very lowest end for humans, if something has a frequency of 20 Hertz, that's just 20 vibrations per second, that's at the lower end of human hearing. Anything below that is actually quite difficult to hear because there's not enough vibrations per second going on. At the top end, at the higher end for humans, it's near 20,000 Hertz, and that's a very, very high pitched sound. Beyond that, we're not able to detect this. We're not actually able to hear it. In actual fact, as you get older, this will actually begin to get lower. At a younger age, you can probably hear sounds of that frequency, but as you get older, that becomes more difficult to do. Now, any sound that has a frequency higher than 20,000 Hertz, we call that ultrasound, and this is the topic of the video, and this is what we're looking at and how it can be used. So here is an example of how ultrasound can be used. We've got a setup here which is called an ultrasound scanner. We've got a little object here which is called a transducer, and the transducer will produce ultrasound waves and also detect them as well. And here we have a control system with a screen which will display any images that you're looking at. Now, the key to this thing working is that, one, it will produce these ultrasound waves which will travel through the tissue, but the ultrasound waves are partially reflected at different boundaries between different tissues. So the way it works is like this. We have the ultrasound waves which are produced, and they are partially reflected when they meet different media. Different media just means different substances of maybe different densities. So the ultrasound waves will pass through. Where they meet this boundary here, they will be partially reflected, and this transducer will measure the time taken for them to be reflected from that boundary. The next thing is that the time taken is measured, and then we have each boundary distance measured, and then we have our image formed. Okay, so there's one boundary there. We've got partial reflection of the ultrasound waves. The second one might be down here, and the ultrasound scanner will actually measure how long it takes for the waves to come back, and it can then take that, make some calculations, and actually create an image of what it is you're trying to look at. So the key here really is that we're using sound waves, we're measuring distances travelled, we're measuring reflection of those sound waves, and a control system with a processor will actually transfer those sound waves into images based on the data that it picks up. Here is a formula that you need to know and to be able to use, and you have to be very careful with this formula because the letters aren't as obvious as you might think. It says S equals V times T. This will be given to you in the exam on the formula sheet, but in this case, when we're talking about ultrasound, the S actually stands for distance in meters. Now that's very confusing because we usually use D for distance, and I have no idea why that is used like that, but this is the formula. S is the distance in meters, the V actually stands for speed in meters per second, and T thankfully is actually time in seconds. So this is a formula that you should be able to use when we're working with ultrasound. And just to give an example, here's a little problem that you might be given to work out. So we have an ultrasound wave travels at 1400 meters per second through body tissue. A detector determines the time taken for the wave to return from a tissue boundary is 0.0001 seconds. Calculate the distance to the tissue boundary. So this is fairly straightforward. We've got the distance equals speed times time. So in this case we would just have to substitute in the formula. So it's 1400 times 0.0001, which is actually 0.14 meters. Now there's a little trick here, be careful, because it says the time taken for the wave to return to the tissue from the tissue boundary. That means this distance is actually double the distance because it's gone to the tissue boundary and come back. So we would have to times that by half to find the actual distance, which is 0.07 meters, which is about 7 centimeters. Okay, so that's one little example that you might need to be able to do, or should be able to do. And what also might be useful is the formula triangle for this. So here's the formula triangle, so you don't have to do rearranging of formulas in an exam if that's what's required. And so that's a formula that you need to know. And the last thing I just want to quickly go over with you is 2 actual examples of uses. You probably know these anyway, but this one example here is what we call prenatal scanning. And prenatal scanning is done at regular intervals during pregnancy, and this is just to see that the development of the baby is going well and the baby is fine and healthy as pregnancy progresses. And we use the ultrasound scanning in order to do that. One other use is while we can get images of kidneys and things like that by our ultrasound scanner, we can actually also use it to treat what we call kidney stones. So here, if I just enlarge that a little bit, here is a kidney, and right there we've got what's called a kidney stone. And these things can develop in the kidney for some people over time, and they're actually very, very painful. Now, in order to get rid of it, one way would be to carry out some surgery and try and pick out the different stones. But another use of ultrasound is actually breaking these down. The ultrasound is used as very high frequency waves, which can be fired at the kidney stones, and they'll actually break down. If you choose the right frequency of the ultrasound, they will break down the kidney stones, and they can then just be passed out of the body as normal. And that's not requiring too heavy medical treatment or any invasive surgery or anything like that. The last thing I very quickly want to go through is just a quick comparison of ultrasound versus using X-rays. And the 2 key things really are that with ultrasound it's non-ionizing. X-rays, as you may have seen in the previous video, are ionizing and can lead to complications, even things like cancer. But ultrasound are non-ionizing, and also with ultrasound you can produce accurate images of the soft tissue. X-rays are less good at producing images of soft tissue, so in that way ultrasound is a little bit better than X-rays. So that's basically me done for this video. Thank you for watching, and I'll see you again soon.